Okay, class, we're about to start section 3.2, like a snowball rolling downhill. Our learning objectives is to describe how compound interest differs from simple interest, to develop compound interest formulas, and to use compound interest formulas to analyze financial issues. Now, Warren Buffett says, my wealth has come from a combination of living in America, some lucky genes, and compound interest. Now we look down here at the bottom. It says we've already studied how an investment can grow when simple interest is calculated. The table below is borrowed from lesson 3.1, borrowed, stolen, whatever. In this case, the principal amount of $600 was invested at 5% interest. Our first goal in this lesson is to recalculate the interest earned and value of the account. This time calculated the next year's interest on the entire value of the account, including previously earned interest, rather than just on the principal amount. Okay, now we move on over to page 218. Okay, number 1. It says compute the amount of interest earned during the second year if that amount is 5% of both the principal amount of $600 and the $30 in interest that was already earned in the first year. Find the new ending value as well. Okay, so first of all, we would do interest is equal to principal times rate times time, just for us to capture the first year. So the principal was 600, the rate was 5%, and the time was 1 year. So our interest was $30. This is where we got the $30 from, just to re-jog your memory. So now, for the second year, the new principal would be the original 600 plus the $30. So your new principal would be $630. So we could use the same formula. The interest is equal to principal times rate times time. So interest, the principal would be 630. The rate would still be 0.05, and the time still would be 1 year. Now, we could put this in our calculator. So we would have 630 and then multiply by 0.05. And we don't have to put 1 because we know times 1 will give us the same thing. So it'll be $31.50. Now that's how much interest we would get the second year. But we want to know what the new ending value is as well. So we would take the $630 we started with, and then we would add the $31.50 to it. So this will give us $661.50. That's how much we would end up with after that second year with the interest. Now, number 2, we know from lesson 3.1 that we can compute the amount of interest earned in 1 year using the formula I equals PR. That is using T equals 1 in the interest formula I equals PRT. Use this formula with P equals 630 to show that you get the same answer you did in question 1. We already did that, so we could just rewrite it. I equals PRT. We said our new principal was $630. The rate is still 5%, and the time is 1. And the interest we already calculated, which was $31.50. Okay, number 3. It says, use your answers from question 1 to fill in the row of the table corresponding to after 1 year. Then repeat your calculations to fill in the remainder of the table. Keeping in mind that in each case, interest should be calculated on the new amount at the beginning of the year. So we know after 1 year, we calculated that already. The interest would be $30. So the value of the account would be $630. The second year is what we got here, this $31.50. So we'll take $31.50 plus the 30. So it'd be $61.50. And we'll add this to the 600. So it'd be $661.50. Now we will have to do the third year and also the fourth year. So we can use that same formula, I equals PRT. So our principal would be 661.50. Our rate would be 0.05, and our time would be 1 year. So we will put that in this calculator here. So we have 661.50 multiplied by 0.05, and we don't have to multiply by 1 again because we know what that is. So this will give us interest of about $33.08. So we will add that here, the $33.08. That will give us $94.58. $94.58. So this would be $694.58. And then we would take this $694.58. So we'll do the formula again, but this time the principal would be $694.58 times 0.05 times 1. And we can put that here in this calculator. So 694.58 times the 5% will give us $34.73 in interest. So we will add that here, and this would take it to 129.31. And we will add that to the 600, so it would be 729.31. So that will be our ending balance after 4 years. If all went well, you should have found that at the end of 4 years, the account will have $9.30 more when interest is calculated on the new yearly amount rather than the original principal. All right, so with that being said,
you are now muted. You are now unmuted.
Okay, this type of interest is called compound interest, and each time the new amount is calculated, in this case at the end of each year, we say that interest has been compounded at that time. Since interest is being compounded once per year in this example, we say that it is interest compounded annually. You're probably not overly impressed by that extra $9, but when we develop some formulas for efficiently computing compound interest, we'll be able to see that something very interesting happens in the long run. So let's get to work on developing a formula by looking for a pattern. Okay, now we move on to page 219. Now it says value after 1 year. It says 600 times 1 plus 0.05. Then the value after 2 years will be the 600 times 1 plus 1.1 plus 0.05 times 1 plus 0.05. So that leads us here. So 600 times 1 plus 0.05 to the second power. Now fill in the boxes in the computation to find the value after 3 years. Now if you look up here at the 1 year, even though an exponent is not here, this is assumed to be taken to the first power. This is to the second power. So then to get the 3rd year, we know this will be to the 3rd power. But to fill in this portion here, we would take the 600 times 1 plus 0.05 to the second power, because this was the value after 2 years. Then we multiply by this value. So if you notice here, after 1, 2, and 3 years, the exponent keeps increasing. So then after 4 years, it'll be the same thing, except for the exponent would be to the 4th power. And then the 5th year, the exponent would be to the 5th power. Now it says, make a conjecture as to the value after t years. When t represents any number of years, value after t years, it'll be 600 times 1 plus 0.05 to the t power. And we know t represents the years. And we have the formula down here. Formula for compound interest compounded annually. And we know A means the future value. So we have the principal times 1 plus the rate to the t power. And we know this rate, this is time. Now we move on to the next page. to number 7. It says use the formula for interest compounded annually to find the future value of the original $600 investment at 5% interest after 10, 20, 30, and 40 years. Then use the simple interest formula from lesson 3.1 to find the future value if the interest is simple. Now, this is what we would do. We need both formulas. So first of all, for the compounded value, it'll be A equals 600 times 1 plus 0.05 to the t power. Now for the simple interest, it'll be A is equal to 600 times 1 plus 0.05 times t. Okay, so now we need to find both of these values. So what I'm going to do here to make this a little easier, I'm going to type this into the calculator. Now I'm going to show you a little trick with the calculator really quick. So what we could do, we could type in these values here, but instead of using A and T, let's use Y and X. And I'm saying for the calculator. So if we type in Y is equal to 600, then a parenthesis, 1 plus 0.05, and we close our parenthesis, and then we would take this to the power of, we'll make tx. So we know y is a and x is t. Now we will go up here to this little wheel, and we will go down here and press this table. So this converts it to a table. Now what makes this table very nice is this here. You could just type in the values in the table. So you could go 10, 20, 30, and then you could do 40. Now, when we get these values here, we know we have to round to 2 decimal places. So for 10, we would add $977.34. For 20, we have $1,591.98. For 30 years, we had $2,593.17. And then finally, for 40 years, we would have $4,223.99. Okay, now that took care of the compound interest for future value. Now we're going to do the simple interest for future value. So we could basically do the same thing. We'll use y for a. So we have y is equal to 600, parenthesis, 1 plus 0.05, and we'll put in x for t. Close our parenthesis. We'll hit this wheel at the top, hit the table, and then we could type in the numbers here. We could have 10, 20, 30, and then 40. So for 10 years, it'll be $900. 20 years, it'll be $1,200. 30 years, it'll be $1,500. And 40 years, it'll be $1,800. Now, it says, use the table to draw a graph of the future value for both accounts. Then write a verbal description of what you learned from the table and the graph. Make sure you choose an appropriate scale for each axis. And of course, label that scale on your graph. Do something to distinguish the two graphs. Use different colors or make one dash or thicker. What kind of growth does each account illustrate? Okay, so what I'm going to do, I got a black pen and a pencil, so I'm going to do it that way. So first of all, the years, we could go by twos here. So this would be 0, 10, 20, 30, 40, all the way up to 50. And then going up here, we could go by 200s. So this would be 1,000, 2,000, 3,000, 4,000, and then 5,000. So I'm going to graph the first portion. So we'll do the future value for the compound annually, and I'll use this pencil. So 0, it'll be 977.39. It'll be real close to 1,000, but not quite there. And then next, for 10 years, it'll be 1591, almost 1600. 24. It'll be very close to 1600. And then for 30 years, wait a minute, you know what? Okay, I made a little error here. Let me go back. I'm glad I used a pencil that time. But even though it's not shown here, the 0 year is supposed to be 600, which is the principal. So that'll be 246. So this would be the 0 year. Then the 10th year would be the one that's close to 1,000, which would be 977. And then the 20th year would be close to 1,600, which would be about here. The 30th year would be close to 2,600. And then the 40th year will be a little bit over 4,200. All right. So if I connect these points, all right. Now, if you notice, it's an exponential regression graph here. Now we go here to the simple interest. Now I use the ink pen here. So still it'll be 0, 600. Then it'll be 10, 900. So 900 will be right here in the center between 8 and 1,000. And then it'll be 20, 1,200, which will be here. And then it'll be 30, 1,500, should be here. And then it'll be 40, 1,800, which will be here. Now, if you look here, this forms more of a straight line. All right. So now it says use different color or make one dash or thicker. What type of growth does each account illustrate? The compounded illustrates exponential growth. The simple interest illustrates linear growth. All right, now we go here to the back. It says, based on what we've learned so far, if you're the one getting paid interest, compound interest is a much better deal for you than simple interest. But what if you plan to invest your money for less than a year? You'd end up getting a whole lot of nothing since the interest is compounded for the first time at the end of the first year. This will provide a competitive disadvantage for a banker, as wise investors would prefer more flexibility. At some point, bankers decided that compound interest more often would make them more attractive to potential customers. So let's say the interest is being compounded 4 times per year or quarterly. Going back to our investment of $600 at 5% interest, the banker would not add 5% to the account 4 times per year. That would correspond to a far higher rate than the 5% they promised. Instead, they divide the rate by 4 and pay 1.25% every 3 months. The first calculation after 3 months will look like this. Now, if we wrote it out as a formula, it'll be A is equal to P times 1 plus R over N. After 6 months, write a calculation that describes the future value using the same idea from the group portion of the lesson. Remember that interest is being calculated 4 times per year. So we would do A is equal to, the principal is 600. So they told us that's what we would start at. Our rate is 5% divided by how many times per year is compounded, which is 4. And then this would be taken to the second power. And I will explain that second power a little later. All right. So we go down here to number 2. By the time the first year is up, the interest would have been calculated 4 times. So the total exponent on the parentheses in our future value calculation will be 4, which is the number of times per year that interest has been compounded times the number of years that have passed. If interest is compounded monthly, after 5 years, it will be compounded 60 times because it's 12 months in a year times 5 years will be 60. If interest is compounded n times per year, after t years, it would have compounded n times t times. Now we're going to go over that a little bit more in depth. So I think it'll be better once we get some problems. So let's go to the next page. Now, just to let you know here, with this next page, we do have a formula down here, but let's do problem 5 first. It says, now adapt your answer from question 1 into a formula for calculating the future value of that $600 investment at 5% interest if interest is compounded n times per year for t years. Remember that the interest rate needs to be divided into n equal portions. So this formula would be A is equal to 600 times 1 plus, we already know our rate, which is 0.05 over n, because that's the number of times it's compounded, to the n to the t power. So for this problem, we would have A is equal to 600 times 1 plus 0.05 over 4, because it says it's compounded 4 times a year, and then it'll be 4 times. Now remember, the time in this problem here is half a year. So the time here would be 0.5. So it'd be 4 times 0.5, and that's how I got the 600 times 1 plus 0.05 over 4 to the second power. All right, now it says here, use the compound interest formula to calculate the future value of our $600 invested at 5% interest compounded quarterly for 10 years. Then compare it to the future value you calculated in question 6 of the group portion using interest compounded annually. So A is equal to the principal times 1 plus the rate over n to the nt power. So we have A is equal to the principal is 600 times 1 plus 0.05 over 4 to the 4 times 10 power. Because remember, n is the number of times it compounded, t is the number of years. So this would give us $986.17. Now they asked us to go back to problem number 6 from the group portion. Now if we go back to problem number 6, actually is really problem number 7 from the group portion from this table, because it says after 10 years, this is how much you will earn if it's compounded annually. So it'll be $977.34. So we could put down here annual compound interest is $977.34. So they want us to say which results in more interest. So the quarterly compound interest results in more interest. Now we could say the exact amount you receive blank more. Now I'm going to calculate that now. So we would take our 986.17 minus the 977.34, and that would give us $8.83 more. So we'll put down $8.83 more. But that's only for the first year. It will increase as time goes on. Okay, now we go here to the back. Number 7. It says repeat question 6. This time using interest compounded monthly, 12 times per year, and interest compounded daily, 365 per year. In each case, find the amount of interest that was earned, not just the future value. So first, we want to take this future value. So we know it'll still be at 5% because that hasn't changed. So now we want to do this 12 times a year. So we add 600 times 1 plus 0.05 over 12. And then we would take that to, it says it's compounded monthly, and it's still for 10 years. So it'd be 12 times 10. So when we put this in our calculator, first of all, that 12 times 10 will give us 120. So our exponent would be 120. Now, when we put this in our calculator, our value would be $988.21. And that means that our interest would be $388.21. Now, the reason why I didn't write this out is because we started with $600. We ended up with $988.21. The difference of these two is what gives you the interest. Now we're going to go over here where it's compounded daily. So you get, for this, you get interest every day. Now that sounds good when people are paying you. So 365 would be our end, and then our exponent would be 365 times 10. So we have A is equal to 600 times 1 plus 0.05 over 365 to the 3,650th power. So A is equal to $989.20. So your interest here would be $389.20. So now it said draw a general conclusion about what happens to the amount of interest as the number of times compounded yearly goes up. Then, and this question really requires some thought, see if you can come up with a reason why this makes perfect sense. A true understanding of the difference between simple and compound interest will really help. So basically, the more times the interest is compounded, the larger the future value. This makes sense because every time you earn interest, you make money off of the new interest. So basically, you're making interest off of your interest. Okay, now we come down here to the bottom. We have the effective interest rate. We've now seen that the number of times interest is compounded per year has an effect on how much interest is actually earned. It's not a huge effect, mind you, but is at least worth studying. The bottom line is that when interest is compounded more than one time per year, the actual percentage earned is a bit higher than the stated interest rate. That's good if you're the lender, not so good if you're the borrower. In any case, there's a formula that can be used to measure this effect. First, the terminology. Okay, at the top of the next page, it says the effective rate, also known as the annual yield, is the simple interest rate which will yield the same future value over 1 year as the given compound interest rate. The compound interest rate is sometimes known as the nominal rate. Now the formula. E is equal to 1 plus r over n to the n minus 1. E is the effective rate, n is the number of times that interest is compounded per year, and r is the nominal interest rate. Okay, so now it says here, a loan has a nominal interest rate of 4%, and the interest is compounded weekly. Without doing any calculations, would you expect the effective interest rate to be higher or lower than 4%? Be higher. And they ask, explain. Compound interest earns more than simple interest. So the effective rate would be higher. Okay, number 10, it says refer to question 9. Calculate the effective interest rate. So we know the formula is E is equal to 1 plus R over N to the N minus 1. E is equal to 1 plus, the rate is 4%, which is stated here. And the number of times it's compounded is weekly. It's 52 weeks in a year. And then that'll be taken to the 52nd power minus 1. So we'll put this in our calculator. I guess I could type it out here. So we have parenthesis 1 plus 0.04 divided by 52. Close that parenthesis. Then we would take this to the 52nd power. Move this over, minus 1. So now, we will round this to 4 decimal places. So it'd be 0.0408. And then we will write this out as a percent. So I should put the approximation sign. So your effective interest rate would be 4.08%. It says find the future value after 1 year for an investment of $10,000 at 4% compounded weekly. So first, let's list a couple things. First of all, the principal is $10,000. The rate is 4%, which is 0.04. The time is 1 year, and then the N is actually 52. So now we would do that future value formula, which is A is equal to the principal times 1 plus R over N to the NT power. So the principal is 10,000. The rate is 0.04. The number of times compounded is 52. Then here this would be 52 times 1. So it would be A is equal to 10,000 times 1 plus 0.04 over 52 to the 52nd power. Now we can put this in our calculator. So we will have 10,000 parenthesis 1 plus let's see, 0.04 divided by 52. And you will close the parenthesis, and you would take it to the 52nd power. And your answer here would be $10,407.95. So that would be our future value. All right. Now we move on to the next page. Now it says here, divide your answer to question 11 by 10,000. What do you notice? So we had $10,407.95 all over 10,000. So we'll do $10,407.95 divided by 10,000. So that would give us, if we round to 4 decimal places, 1.0408. So this, say, what do I notice? If I subtract 1, then I will end up with the same effective rate as in problem 10, which is 4.08%. Now it says comparing investments is a very important part of any financial strategy. Which saving account is a better investment? 6.2% compounded daily or 6.25% compounded semi-annually? There are different ways you could approach this, so make sure you show all work and explain how you made your decision. So the best way to do this is to find the effective interest rate for both. So first of all, this first portion here, they gave us the percent and they also gave us the time. This is compounded daily and this one is compounded semi-annually. So we had E is equal to 1 plus R over N to the N minus 1. So we're going to do the first one. So it'd be 1 plus, the rate would be 0.062 all over N, which would be 365 because it's compounded daily, to the 365th power minus 1. Now I'm going to write the other one, start that one off too. So it'd be 1 plus R over N to the N minus 1. So it'd be 1 plus, the rate would be 0.0625 all over N. It says semi-annually, so that would be twice. And then that'll be taken to the second power minus 1. So now we're going to put these into the calculator. So we have parenthesis 1 plus 0.062 divided by 365. Then we're going to take that to the 365th power. And then we will subtract 1. And then this will give us 0, we'll round to 4 decimal places, 0.0640, which is approximately 6.4%. Now, that took care of the first. Now we go here to the second. We put in this value here. So it'd be 0.0625. And then your denominator would be 2. And your exponent would be 2. So when we put this round to 4 decimal places, we had 0.0635 which is equal to 6.35%. So as you see here, the compounded daily earns more. Even though the compounded semi-annually had a higher interest rate starting out, but over that year, the effective rate was higher for the compounded daily. All right, now we come here to the next page. It says interest compounded continuously. The goal of the remainder of this lesson is to see if we can figure out what happens to the compound interest formula when the number of times that interest is compounded per year gets really, really large. Large to the point that in essence, interest is being compounded every instant of every day. Wow. As you know, the compound interest formula is A equals P times 1 plus R over N to the NT power, where N is the number of times per year that interest is compounded. To rewrite this formula in a form that makes it easier to decide what happens when N gets really big, we're going to introduce a new variable U, which we would define by U equals N over R. First, solve the equation to find a new name for N. Okay, so we will have U is equal to, it tells us N over R, and they want us to find a new name for N. So they want us to get N by itself. So what we will have to do is multiply each side by R, and then we will have RU is equal to N. So you could put NU, N is equal to RU. That's what N is equal to. Now, replace N in the compound interest formula with the new name for N that you found in question 14 and simplify to show that the formula becomes this here. Okay, so we have A is equal to P times 1 plus, it'll be R over N to the NT power. So we're going to put RU in its place. So we have A is equal to P times 1 plus R over RU to the RU T power. Now, going up here, we have A is equal to P times 1 plus. These R's will simplify out. And what you will be left with is 1 over U. And then you will have it, now RUT and URT is the same thing. So I'll put URT. So this is how you get that formula. So you really didn't change anything. Now it says explain why this can be rewritten as A equals P times parentheses 1 plus 1 over U to the U to the RT. Now in order for you to know this, you need to know the exponent rule. The exponent rule of power to a power utilizes multiplication. Whenever a power is taken to a power, you can multiply the powers. And look in here, this U is taken to RT, so you can multiply them and that will give you URT. So that's basically what it's doing. Okay, 17. Remember that U is equal to N over R. What happens to this fraction when N gets really big? Okay, so basically, since N is in the numerator, as N gets larger, and if R is greater than 0, then U would get larger. Okay, now we go here to the back. Here's a summary of what we learned in questions 14 and 17. The compound interest formula can be rewritten in the form below, and as we make the number of times that interest is compounded per year get larger and larger, the variable u in that expression gets larger and larger as well. So next we'll study what happens to the expression inside the brackets when u gets larger and larger. And we'll find that we can find a much simpler form for this formula. It says, using a calculator, fill in the table below, round to 3 decimal places. What can you conclude about what happens to the value of 1 plus 1 over u to the u as the number of compounding periods tends to infinity? Okay, listen. They want us to fill in this table. So what I'm going to do, I'm going to put in this formula. But like I said, I'm going to use y equals, and the u's will become x's. So we can make a quick table here. So it'll be y is equal to the parenthesis 1 plus 1 over, I was supposed to put 1 divided by x. 1 divided by x. Then move this this cursor here. Then we'll close the parenthesis, and then we would take this to the x power. Okay. Now, we have this formula here. We'll go to the wheel. We'll make this table. Okay, so now we have the table. Now we could type in values. We could do 50. What's that? 100, 500, 1,000, 1,500, 2,000, and then 2,500. All right. So we have all those values, and we could put in the values here. We could round to 3 decimal places. So it'd be 2.692. It'll be 2.705. Let's see, 2.716, 2.705, 2.717, that 2.718, and 2.718. All right, so they ask us to talk about this as we go to infinity. This tends to go to 2.718. That's what it seems to be going to. It says here, oh, you know what? I made a mistake here. I put 100 instead of 1,000. So that should be 2.7. This should be 2.717. All right, the number that you should have found in question 18 is about 2.718 and is denoted E. Actually, E is irrational, so it's a decimal equivalent, neither terminates nor repeats. So E is approximately 2.718. What is the result of the compound interest formula above when the number of times interest is compounded gets larger and larger? In this case, we say that interest is compounded continuously. You could think of this as the interest being compounded every instance of every day. So listen, basically, if we write out this formula from up here, okay, what we did down here was basically take this bracket, and we're told here that this bracket is basically equal to E. So our new formula would be A is equal to P times E to the RT. Because this right here, E, is what's equivalent to it. So now, we would take this information and move on to our last page of the day. Say 20, it says use the formula you wrote in question 19 to find the future value after 20 years of a $5,000 account that earns 4% interest compounded continuously. Then compare that to the future value of the same account if interest is compounded annually. So we know the continuously formula is A is equal to P times E to the RT. So we're told that we're given $5,000, which would be our principal, times E. Our rate is 4%, which would be 0.04, and our time is 20 years. Now, when we put this in our calculator, we will get approximately $11,127.70. Now, that's continuously. Now they want us to do annually. So annually, we know A is equal to P times 1 plus R over N to the NT. So our principal is still 5,000. Our rate is still 4%. Our N is 1. And then we add 1 times 20. So we know our exponent will be 20 here. So when this is all said and done, our answer would be approximately $10,955.62. So if you notice, the compounded continuously actually works better. It says, finally, let's compare interest compounded continuously to simple interest. Suppose that $50,000 is invested in two accounts. One earns 6% simple interest, the other earns 6% compounded continuously. Fill in the table with the future value of each account after each term. Round it to the nearest dollar. Wouldn't this be a great spot to use a spreadsheet or at least a table feature on a graphing calculator? Okay, first of all, the compounded continuously, this is the formula. It'll be the 50,000, which would be your P, times E to the RT. R would be that 6% times T, and T would be these numbers here. Now the simple interest, it'll be the 50,000 times 1 plus 0.06 times T. Now, of course, as you all know, I'm big on using the tables here. So what I'm going to do here, this table here, if I'm not mistaken, this was already, well, that's not the simple interest one. This one here is in simple interest. So I'm going to type in the 50, well, let me just go ahead and do this all the way. All right. So I'm going to make AY, so it'll be Y is equal to, I'm going to do the simple interest first, parenthesis 1 plus 0.06, 1 plus 0.06, and we're going to make the TX. And then we're going to hit this wheel here, go to a table, and we're going to type in the values that we have here. We have 5, we have 10, 15, 20, 25, and then 30. All right. Actually, sorry, I made a little error here. I did not put the 50,000 on the outside here. All right, so that makes the difference. Okay, so now that we have this here, we could type in these values or write them out. So at 5 years, it'll be 65,000, and we'll write out the rest: 80,000, 95,000, $110,000, $125,000, and then $140,000. All right. So that took care of the simple. Now we're going to do the continuous. So we have y is equal to the 50,000, and then we would do the letter E, and then we would take this to the power of 0.06x. We would get the wheel, do the table, then we would type in those numbers. We would have 5, 10, 15, 20, 25, and 30. Now sometimes you got to hover over the numbers here because sometimes it'll have more digits than what's shown. But it looks as though it doesn't have that issue. So we will write these values in. We'll start off with $67,492.94. Then we have $91,105.94. We have $122,980.16. Let's see, $166,000. 5.85, 224,084.45, then 302,482.37. Now all these are supposed to have dollar signs because this is money. Okay, so as you see here, the compounded continuously, it ends up being way more than the simple interest as time goes on. And we are done. If you have any questions, please email me. And please don't forget to do the check assignment today. And remember, your project is due tomorrow and the worksheets are due tomorrow for 3.1 and 3.2. And that's project 2 that's due. All right, have a wonderful weekend.